really pleased to introduce Dr. Makoto Kelp. Makoto received his BA in chemistry from Reed College with research experience pertaining to air pollution monitoring and secondary organic aerosol modeling, and then moved ahead to completing a PhD at Harvard, where he focused on expanding the capabilities of atmospheric chemistry models and quantifying various aspects of air quality. He now works as a NOAA Climate and Global Change postdoc fellow with the Climate and Earth System Dynamics Group at Stanford University, and his current research centers on studying the impact of prescribed fires on smoke exposure at high spatial resolution to advance the mechanistic understanding of prescribed burning efficacy in a warming climate, and to develop strategies that mitigate socio-ecological impacts of wildfires. In addition, in his spare time, he plays jazz trombone, enjoys football, basketball, and horror movies, which I'm a big horror movie buff too, so I appreciate that. So with that, I'm going to stop sharing the screen and hand it over to Makoto.
Great. Thank you for that nice introduction, including my hobbies from my website. They're always appreciated. Okay, can you see my screen and hear me? Everything okay? Okay, perfect. Thank you everyone for your attention. I'm really happy to give this talk to a group of people who are sort of more tied into the management of fire and not just simply in academia. And I'd like to acknowledge several of my co-authors here, being Matt Carroll, who works for the United States Forest Service, Tina Liu, who's a postdoc at UC Irvine, Heath Hockenberry, who's at the National Weather Service, and Bob Yantoska and Loretta McLeay, who are at Harvard. And so I start by saying that the West has always burned. So pre-European intervention, pre-European colonization, I'll let you choose that word on your own time. There's really a routine indigenous land management in America. It's been a cultural practice of having these prescribed burns for thousands and thousands of years within these communities. But really, within the last 100 years or so, fire suppression has been the law of the land. Starting with the turn of the 20th century, we have the establishment of the United States Forest Service, national forests and parks, and we really want to conserve and safeguard these natural areas by suppressing fires. Within the early 1930s, we had several severe fire seasons in America that led to the rise of our lovable sort of anti-hero mascot in many ways, Smokey the Bear, where it wasn't just enough to put out fires as quickly as possible, but you have to start actively preventing them. Only you can prevent these forest fires. Coupled with the rise of American environmentalism in the 1970s, we have increased use of environmental lobbying that led to wide-scale shutdowns of sawmills and logging companies throughout the Western US that really left us without a large-scale regional infrastructure to remove hazardous fuels. This crescendoed within the wildfire seasons of 2018, 20, and 21 that many of you in the West are very familiar with, that have been one of the most destructive on record. And this has culminated in August of last year by the Biden administration and Congress passing the Inflation Reduction Act, in which nearly $2 billion has been designated for the reduction of hazardous fuels, including a large emphasis of increasing the use of prescribed fire. And really today, we're in a fire deficit where we're burning only 10% of what we were burning pre-European. And just to give a larger set of context here, we find that this fire deficit and how these fires are being ignited is a really tricky kind of problem. If you look on the left figure, we see that the mean fire size of fires that have happened over the last several decades are much larger in the Western United States than in the East. A lot of this is because of these kind of large, pristine forests that we have preserved. On the right, we see how these fires are largely ignited, and most of them are driven by humans. And there's a certain randomness to ignitions. These fires can happen anywhere from a fallen transmission line to a flicked cigarette butt. Whereas lightning, or what we can consider a natural source of fire ignition, is much lower in frequency. And although lightning is pretty random in some ways, it's tied to weather and convective events, we kind of understand hotspots of where lightning occur, whereas that of human ignition is much harder to predict. As a result, these human ignited wildfires are also more destructive, largely because they damage infrastructure. They're closer to where people are living, and so they have a larger effect on society. And this, coupled with the sort of randomness and the general foolishness of human behavior, we're left in a weird situation in which the West is basically a tinderbox that can be lit at any moment, and it's really hard to predict when, where, and how that may happen. Okay, and so we know that fire is devastating in terms of damage to human infrastructure, but there's also this health impact of smoke. And we know that over the last several decades, in America, at least, we have really cleaned up our air quality. Air quality has been getting cleaner in cities. We've put scrubbers in power plants and catalytic converters in cars. And generally, air quality has been getting cleaner in the US in both urban areas, traffic sources, and these large power plant sources. But with those air quality regulations, now we have this rise of smoke pollution, smoke PM 2.5, that is really undoing a lot of this air pollution gains we've been getting. So we know smoke is this large impact on human health, and many people are wondering, what's the contribution of climate change to this system? And it's still really being studied. This is a paper that's in prep from Shufeng, who's a postdoc with Loretta Mickley, and is finding that climate change is a significant driver, contributing 30 to 80% of wildfires in the West, depending on which ecoregion you might be in. But, I'd round this off to 50%, meaning 50% is from climate-driven change of hotter temperatures, drought-like conditions, sparking fires. But that means the other 50% is really this societal constraint of fire suppression. So it's this really, this balancing act of these two systems kind of colliding with each other. And so prescribed burns is really still a boutique application in the Western United States. So it depends on which state that you're in. These policies are different state by state. I know that it's more common in the desert Southwest where you are, but it's still not really very common in the West Coast, where a lot of these wildfire events and large smoke events are emanating. We see here that the green indicates prescribed burn acres, and red being that of wildfires in terms of total burned area. We see that in the West, most fires are wildfire in nature in terms of total area burned, whereas in the East, it's largely more managed fire. This is especially true in the southeastern United States, where prescribed fire is very, very common. If they don't do prescribed fire every year or every 2 years, the ecosystem can drastically change. You see these big circles in Texas, Oklahoma, Kansas. This is largely agricultural controlled burns here. But you can see that between East and West, there is a very large divide. I have a quote here from Jason Sachs, who works at the EPA. He's heavily invested in fire and regulations, and told Loretta Mickley and I that right now within the EPA realm, that the biggest policy issue on the table is prescribed fire. So there is this large demand to understand the efficacy of it. Okay, and so many in here are familiar with some tools that we use to study wildfires and the transportation of smoke. Here, I'm going to highlight a very commonly used tool. They're called Lagrangian dispersion models, or PUF models. Many of you might be familiar with high split. It's a widely used model to show how the air arriving at your location of interest is influenced by different regions depending on weather patterns. So basically how it works is that I have some kind of receptor of interest. This could be your own urban airshed. It could be an area that you want to study. So you define that grid. And then you have these different weather fields over time. What you do is take your air parcel and run your box backwards in time depending on the weather conditions you have. And you generate an ensemble of different trajectories. That's what you kind of see in the bottom left corner here. Having some kind of receptor of interest in the Midwest US and seeing how that air has traveled to come to your location. What you can do then is conglomerate all those different trajectories and create what we call a footprint here. And here I define a footprint as the upstream area that influences the air arriving at your location. So what this looks like is if my location is this black circle here, and the footprint is the influence of this region to influence air quality in your ultimate destination here. So the brighter colors, meaning that emissions in those areas have a larger impact on your local air quality. And this has been really a common tool in the scientific literature, where we have long-range transport shown here over the United States. On the right is different agricultural fires on air quality in India. And in fact, it's so pervasive that the United States Forest Service has incorporated this into their Blue Sky Playground, where you can quite literally run high split within a web browser. So in many ways, it's this nice democratizing, easy to use tool that you're able to study the transport of air pollution. And I think it's a really great tool. However, I think in many ways it's being overused. I think stilt and high split are pretty simplified examples of transport. You know, there's no effect of wet deposition. So, you know, we know that smoke can get rained out. That's not found within high split. We know that there's chemistry involved. Chemistry can kind of produce and destroy these chemical pollutants as it ages over time. That's not represented at all in these models. And so what I will show here is using a chemical transport model, which has greater physics-based and chemistry-based processes where we can look at how chemistry and how the effect of weather influences smoke. Here I'm showing you examples that have been used in Southeast Asia to study peat burning fires. And this has been shown to determine the concentration, population-weighted concentrations of PM2.5 smoke from these fires. It is able to show the ability of weather to modulate smoke exposure. Can it rain it out? Can it make it travel even farther? The effects of stagnation and such. And also, we can use these kinds of models to have different intervention scenarios. So what does air quality look like during a business as usual peat burning scenario versus one in which restoration policies have been implemented? And I'm going to walk you through how this model works, and the results that I'm going to show throughout this talk is based on this model. And, you know, I want to stress that this is a really important kind of way to examine this air quality modeling of smoke. This is a model, and these chemical transport kind of climate-based models have so many decades worth of people spending their entire PhDs just on a little snippet of a model to study dry deposition of a single particle or a single species. So I think there's just the vast collection of human knowledge in these models is really inspiring to me, and that's what really got me into the field as a whole. But I'll show you how this GeosChem adjoint model works. First is I identify my region of interest. Similar to the Lagrangian model here, but it's a grid-based system instead of a trajectory-based one. So I choose different states and clump them together into ecoregions throughout the Western United States, and also look at certain rural environmental justice communities, being the Central Valley and the in California. This is an area that basically grows America's fruits and vegetables. There's huge populations of Hispanic agricultural workers where inhalation of smoke is this heightened occupational hazard. Similarly, I'm from the Seattle area originally, and we know that there's a lot of agricultural workers in central and eastern Washington that picks a lot of apples. You know, Washington State produces the most apples in the country. And the Navajo Nation. So this, I think, is a very interesting one. This is the largest Native American reservation in America in terms of landmass and population. It actually has very clean air pollution generally. It's in the middle of the desert. There's no large-scale industry that kind of constitutes a large polluting source. So any enhancement of air pollution from smoke would be interesting to study this kind of area. Okay, next is we define some kind of biomass or wildfire burning emissions. Here we use the GFED emissions. It's a consumption or activity-based emissions that maps burned area to smoke concentrations, basically. We do so for the 2018 and 2020 fire seasons, going from July to November. And this is specific to only biomass burning. Next is we generate concentrations of these wildfire-specific pollutants using the geoschem model. So basically, we take this model that has a bunch of different physics and chemistry-based operations, feed in the emissions in time and space to then generate these concentrations. Here I'm showing you, I note here that the resolution is 0.25 degrees, so that's around 25 kilometers squared for the grids that I'll be showing you here today. Okay, and so this is an interesting part here. So we can generate these concentrations, but then we can also generate the effect of weather on these concentrations. I'll call these sensitivities for the rest of the talk. A sensitivity here is defined as the change in concentration of our wildfire pollution of interest, given a change in emissions. And it's computed using this geoschem adjoint. So basically how this works is I run my simulation forward in time. You know, I map emissions to concentrations. I do that for the entire fire season. Once that simulation is over, I then run the model backwards in time, where I basically compute a derivative. So the derivative is the change in concentration due to the effect of these three different parts of the model, being convection, advection, and deposition. So the ability of these three specific processes to affect concentrations of smoke. And the resulting map I show is here. This is for the Northern California receptor that I showed earlier, where the darker spots show an influence of how weather can affect the concentrations of our smoke species. And so, you know, convection and advection are also tied to the topography, which we are not able to get either with the high split kind of model. Okay, and with that, using all these different kinds of informations, concentrations, emissions, and sensitivities, we can calculate population-weighted smoke exposures with this framework. Okay. And, you know, happy to answer any questions about this modeling framework. It is a bit specific, but I think the tool itself is pretty powerful. So I'll show you what that looks like in terms of results. Here on the x-axis is the different months in the wildfire season. It's going from July to November for the 2018 and 2020 wildfire seasons. Each of these color-coded lines represents a different receptor that I showed you, with the dotted lines being one of those rural environmental justice communities contained within a larger receptor. On the y-axis, it's on a log scale, I have to note. This is the population-weighted smoke exposure for these different receptors. And so for 2018, we see that the high of that fire season was due to the Camp Fire near Paradise in Northern California. We see here the blue line. I'm not sure if you can see my mouse, but we see here, okay, great, that the entire Northern California receptor experienced around 44 micrograms of pollution of PM2.5 from smoke averaged over that entire month. And that actually agrees pretty well with surface sites that we have information from. If we look at the Western United States as a single receptor as a whole, we find that over that month, the entire West experienced 8 micrograms per meter cubed of pollution of population when weighted smoke exposure. So just that one fire alone had an 8 microgram effect over the entire Western US. We look here in September of 2020. This was a lot of the Labor Day fires where basically the entire West Coast was on fire. And we see that the high was in September. The entire West actually experienced 44 micrograms averaged over all space and time for that month, which is unhealthy for sensitive groups for that level of air pollution exposure, with Northern California and Washington and Oregon being even higher than that. And so, I think this is good to see that these time series agree well with what actually happened in real life. I don't think it's particularly interesting in many ways because, this is almost common sense to many of you in this audience who already know the fire season dynamics. These are based on emissions inventories, which are really well vetted, and they use satellite data to kind of confirm what has happened in real life. So it makes sense that it matches reality pretty well. So this next slide is the same idea, but we think about this in terms of how random ignition of wildfires are, because it's largely human driven. The campfire could have happened in August of 2018, or the Labor Day fires could have happened in November, because a lot of this was human sparked. We know that, for example, the campfire was due to a fallen transmission line that could have happened at any time. And so what we do here is fix the highs of those fire seasons, being November emissions for 2018 and September for 2020, but we let the weather vary, these sensitivities vary to see how the effect of weather to alter smoke exposures. And we see an interesting result where we find that in 2018, that campfire, that was the worst possible time for that to have happened within this fire season. Later in the fire season, we have more meteorological stagnation than we do earlier in the fall and later in the summer. And so because of that, smoke exposure was the absolute highest to have happened in November for Northern California and also the Western US here. 2020 is a little bit of a different story in which for the Pacific Northwest, that September was the worst time for this to have happened, whereas all the other receptors, if these fires were to have been ignited in October or November, concentrations would have been 30% higher even. A lot of this, again, due to meteorological stagnation later in the season. One that I want to note that's interesting is the Navajo Nation here, that if these fires were to have happened in October instead of September, that they would have experienced 5 micrograms per cubic meter for averaged over that entire month of October. And that might not sound a lot to you, given how high these other West Coast states experience. But basically, this would double their natural baseline exposure from wildfires 1,000 miles away. So it's really interesting to see these long-range transport effects to rural communities in the desert, based on high-emitting events that are found in Northern California, for example. Okay, now I get into talking. Here, I want to highlight again this idea of meteorological stagnation. A lot of this is driven by what's happening in California, where throughout the summer and later into the fall, we have these Diablo winds. These Diablo winds ventilate the Central Valley. The Santa Ana winds push from the west eastward into Southern California. And they typically, not always, start going away in November, which we're seeing here. So actually, it's an interesting thing that the campfire in 2018, the Diablo winds played a huge role in which they both spread the fire early in November. So the fallen transmission line, it was windy, the fire spreads, and then the Diablo winds dissipated in mid-November. And then that just caused a large stagnation event that drove concentrations up really high. And so I want to highlight that the West Coast fires that we find really control the burden of population-weighted smoke exposure throughout the entire Western US for 3 reasons. One are these prevailing westerly winds. We know that due to the rotation of the Earth, that winds go from west to east, so the coast inland. So any smoke that is produced in the West Coast states are pushed inland, whereas the opposite is not as common. Two, there are large population centers along the coast. This kind of skews these population-weighted metrics to these larger cities, which are found on these coastal states. But, this is something that we have to think about because we care about where the people live. And three, there are much denser vegetation loads west of the Sierra and Cascade Mountain ranges. So we have really heavily forested areas in Northern California. The Sierra's over here, a lot of the forests in the Pacific Northwest, whereas going between here and Colorado, the vegetation is a lot shrubbier, and so that produces less smoke when burned. Okay. And so, as many of you might know, being involved with fire research and different agencies in this consortium, that databases and understanding of prescribed fire in terms of an open data setting is pretty limited. A lot of academic papers on prescribed fires are small in terms of area and scope, usually looking at a forest level or an understanding of the canopy dynamics of wildfires or how fires may jump from different fuel types. And so there's nothing that really covers vast landscapes in the Western US. So here, to try to mimic our understanding of prescribed fires, we do a hypothetical modeling scenario. So I found that depending on, the species type in a forest, that prescribed burns can reduce the probability of fire by 25 to 75%. So that's a huge range that I've found. If others here know of literature they'd like to share with me, that'd be awesome. But, for our hypothetical scenario, we said, okay, if this receptor would do a prescribed burn, let's say that would reduce emissions by 50%. It's arbitrary, but it's where these 50% reductions happen that is actually quite interesting. So if I apply a 50% reduction of emissions everywhere, then it makes sense that your smoke exposure would go down by 50%. But let's look at Washington and Oregon here. If all these different receptors in the Western United States reduced emissions by 50% through a prescribed fire intervention, it would reduce pollution by 70-ish micrograms. Okay, but of that 70 microgram reduction, 91% of that would be just doing those prescribed fires in Washington and Oregon alone, with the other 9% coming from Northern California. Similarly, with Northern California, doing those prescribed burns locally has a much larger effect than those influenced from outside states. But once we go inland, so let's look at Idaho and Utah, these Great Basin states, we find that doing these prescribed burns in this local receptor constitutes only 11% of that possible reduction, whereas over half would come from Northern California alone. And that generally in the United States, again, we're seeing these kinds of relationships in which the West Coast really can, just doing those prescribed burns on the coast has a huge effect for air pollution for all of the Western US. And again, you might say that's pretty arbitrary, but I've played with these numbers, and even doing a 10% reduction on the coast and a 75% reduction in these other receptors, we still see these same kinds of patterns. Also, I want to highlight again this Navajo Nation case study. It's interesting that the Northern California Pacific Northwest constitutes over half of that reduction, again, from fires, from prescribed burning interventions 1,000 miles away. Okay, and this might be kind of inundating you with too many plots here, but I would just want to stress how much red and blue that you see in all these different receptors. So you see along this main figure here, where this main figure shows the sensitivity of these different, the sensitivity of weather to influence these different areas, along with the black dots are the locations of fires for September 2020. So you do see that the West Coast in this month was really lit up in fire. And although there were fires throughout the entire West, this just had a huge effect on the Western US as a whole. And we've done this for other months and basically find very similar kinds of relationships. Okay, so you might not be particularly interested in a hypothetical burning scenario. So let's actually look at prescribed burn data that we have. So these black dots that you see on this figure are satellite-derived locations of large prescribed burns. Large being they're over 1,000 acres, which is around 4 kilometers squared. You see that the locations of these burns vary from state to state. You see in the Southwest, where many of you are, it's a pretty well-used tool. Here I find a lot in the Tonto and Apache Sitgreaves National Forests. In Central Oregon, this is largely agricultural burning. The pixelated map that you see is for this really bad wildfire season month of September 2020 and the emissions of smoke. And you see that there is a mismatch between where these aggressive prescribed fires have been done versus where all the smoke was generated for this really bad fire month. See, and there more research needs to be done at a finer resolution, but there is this kind of relationship we see that maybe larger prescribed burns may reduce smoke impacts from future wildfires, but they're really not occurring in these key areas being Western Oregon and Northern California, where we only find 7 of these kinds of fires over a 5-year time period. And you might say, hey, I actually know a lot about forest land management and definitely know that there has been more than 7 prescribed fires in Northern California. And you're actually right. However, a lot of these prescribed fires done in these regions are very, very small. So here is a different kind of data set. This is the NF-PORS data set. It's managed by the Department of Agriculture and along with the Department of the Interior, managed through the United States Forest Service. And it's these fires are reported by land managers. So it's an on-the-ground data set. We find that over a 3-year period, we have this data for 2018 to 2020. Northern California actually had almost 10,000 prescribed burns, but most of them are just so small, on the order of 10 acres or so. If we filter the number of fires by acreage, and looking again at the 1,000 kind of acre threshold, we see a similar relationship to that satellite data. And that even a 500 acre threshold, we find that less than 1% of these fires in Northern California are 500 acres. And that the United States Forest Service, in trying to plan for ramping up the number of prescribed burns in this decade, really want to try to start advocating for applying a small number of large prescribed burns instead of many smaller ones. And I'll talk to you about the feasibility of that kind of later in this talk. Okay, and so another thing I want to highlight is that there's a seasonality to when we're prescribing these burns. And, this data set isn't completely vetted in the sense that some of these are controlled agricultural burns, so they're not all kind of managed land prescribed burns. But we generally find that most of these burns are occurring very late in the year, in October, November, and December, when stagnation effects are actually quite large. A lot of this is due to the seasonality of the workforce who do these prescribed burns. A lot of these people are only available in the summer to late fall. And then once that season is over, they go to the Northeast and work the ski lifts. So there's actually an interesting seasonal effect of the workforce here. This is in stark contrast to the Eastern US or the Southeast US, in which most of these burns are occurring in the spring when fuel loads are still wet and the potential for an escaped fire is lower with kind of low winds. Okay, And so here I want to go over some of the social ideas of prescribed fire. And, in many ways, this isn't a science problem. We have a co-author on the US Forest Service on this paper that said that, prescribed burns isn't a science problem. It's a socio-ecological problem. Many of you in this consortium might be familiar with these ideas, but I think because this is eventually going to be on YouTube, so I think it'd be nice to kind of educate the world that fires are not always 100% a climate change kind of problem. So first is that most fires in the Western United States occur on federal lands, so these national forests and parks. And it actually takes 4 to 7 years to plan and approve a prescribed burn on federal lands through the National Environmental Policy Act. This was a piece of legislation introduced in the 1990s to try to get a larger scale community input, environmental lobbying, and kind of get a consensus on when, how, and where to do prescribed burns. But as a result, it's introduced a huge bureaucracy into the system that really slows down the ability to prescribe fire. So I'm not sure even how this is going to be happening within the next decade with this Inflation Reduction Act policy here. So there's this huge bureaucratic way to prevent large-scale prescribed burns. There's large-scale fatigue and hesitancies of increasing the use of prescribed burns in the West. These fire seasons are getting longer and longer. People are really tired of breathing in smoke and adjusting their lifestyles. And now when that fire season's over, you're going to tell them that you want to burn more fires on purpose. So there's this societal worry of this, and people are not always on board. So communication of short-term costs of prescribed fire are very important. And many people here in the Southwest are very educated on the fact of that these prescribed burns might escape, especially the one last year in New Mexico that was a planned prescribed burn and escalated into a full-on fire that was the largest in state history. So this is always a kind of a case study story that the media and others might latch onto that really scare off the expansion of prescribed burns. In this country, environmental lobbying has played a huge role to dampen this also. In the Western United States, sawmill infrastructure is at a 70-year low. The demand for non-timber wood products is very underdeveloped in the West. If you cut down a tree in a national forest in Oregon, the closest sawmill is in Idaho. By the time you transport that log over there, it's not worth any money. Most national federal lands in the West are too steep, too distant from towns and roadways to bring in heavy infrastructure to prescribe burns or even have mechanical thinning. There was a prescribed burn planned earlier this year in the about 20 miles from Sacramento. It was a 500-acre burn, so 2 kilometers squared. It took 60 people. It requires a lot of resources. It's Northern California especially is very mountainous. It's very close to population centers, and there's a lot of risk involved. Also, it's kind of within our cultural zeitgeist that environmentalism is highly tied to conservation and saving land from being burnt down, saving land from being cut down. We see this in kind of our cartoons that we grew up with, where the trope of chaining yourself to a tree to save the forest is a very noble thing, whereas prescribed burning and cultural burning from indigenous communities is perhaps something that should be highly incorporated in us moving forward and trying to change this culture of what it means to be an environmental kind of conservationist. It's not meant to safeguard land, but to manage it. Okay, whoops. Okay, so another thing is that our infrastructure and sensors to measure air quality is also underdeveloped today. Again, this is tied to government, where government bodies are slow moving. This is a paper that I put out last year with Loretta Mickley, looking at the EPA sensor network today and how it's actually doesn't capture the inhalation of smoke correctly, or the drivers of smoke in the Western United States today. We're not placing enough sensors in locations that measure smoke correctly. We propose a corrected network here that pushes a lot more sensors in the San Joaquin Valley and in Northern California. There's also different air quality regulations where the smoke from wildfires is not accounted for in areas that are out of attainment because they're not able to be controlled by humanity, basically. So it's considered an anomalous event. We're not actively incorporating those metrics, and we're not monitoring them spatially correctly. So there's this potential. We're actually not even understanding the health effects on these different communities. On the right is a paper by Miriam Marlier at UCLA, finding, again, what we found, that there's a mismatch between where smoke is occurring, where these agricultural worker populations exist, and where these sensors are measuring. There's a huge mismatch, so we're not actually able to even quantify smoke correctly. Okay, so last thing is that there is a huge risk for firefighters. You know, in America, we've suppressed fire for 100 years, and we've actually suppressed it quite well. It's sacrificed a lot of firefighters' lives. And right now, no one really wants to work on prescribed fires. The pay is low. The job is incredibly risky for the reasons I outlined. Matt Carroll, who is a co-author, is a communicator in the Forest Service, and there's a bit of a monoculture in the workers who are doing these burns, and it's not the most inclusive environment. He's actively trying to change that, so it's very hard to recruit more people. We know that prescribed burning windows are shortening due to climate change, and again, it's a very high-risk kind of job. Also, this I thought was an interesting piece. Last year, a United States Forest Service worker was arrested because he let a prescribed burn escaped on him. So now there's this even fear of incarceration. So it's a very tricky kind of situation we have. And this is going to be my last slide, just so we have time for questions. Is you might say that the modeling approach I've shown you so far is not really enough to understand how to tackle prescribed burns at a very fine level. You know, this is what I was showing you was 25 kilometers grid boxes, so quite large. Right now, and what I'm working on the next year at Stanford is trying to look at this at very fine spatial resolution, so 3 kilometers squared resolution on different parts of the Western US. We're using physics-based chemistry weather models. We're incorporating dynamic vegetation models to try to model different types of vegetation, being from our dense forests to shrubbier vegetation, and then trying to simulate how prescribed burns would act under different weather scenarios. So we're then able to come up with prescribed burn plans in a ecosystem and in a climate in which prescribed burning windows are getting shorter and shorter. And with that, I leave my key points up here, along with resources from my website. And if you're interested in the paper, it goes more in depth through these methods that I talked about, and it can be found also on my website. But thank you so much for your attention.
Wow, thank you. That was awesome. It took us a lot of places. I really appreciate the presentation and delivery. Like Rachel just said in the chat, if you have any questions, please type them in the chat. We do have one question from Devin here, and I'll read it out. So when is prescribed fire assumed to occur relative to the fire season that experiences the 50% reduction of smoke? And connected to that, does that reduction include the emissions from the prescribed fire burning itself, and how long might those last? So I'll let you jump in there.
Yeah, so we're not actually simulating the physical prescribed burn here. It's just way too coarse of a model resolution. And even then, this model is pretty expensive to run. So we're not simulating the actual prescribed fires. That's something I'm going to be working on with this last tool in the next year. But yeah, honestly, it's a very simple kind of model. It's a simple kind of simulation in which we say that the effect of prescribed burn is reducing the emissions of that wildfire scenario. So in a way, it's a big assumption, but I don't necessarily want to focus on the exact number and the reduction of the teragrams of smoke that might be emitted or carbon. It's more of looking at these different relationships to one another. I guess a big idea or what we wanted to determine is where should we target these prescribed burns that would have the largest benefit. I guess that's how I would reframe it. But yeah, in terms of actually seeing the effect on emissions and prescribed fires, we need a much finer grid model, and that's the next steps I'll be working on.
Great. We just had another question pop up, but I will jump in with a question if everyone allows me. And this one has to do with applying lessons from the large, kind of half continent size modeling that you just shared. And maybe my question's more for breakout rooms on another time, but how do you apply what you just learned from what you presented to prioritization? We're talking at scales bigger than states, bigger than a national forest or even a Forest Service region. And I'm using the Forest Service just because they popped up as one of the biggest burners in the Western U.S. Should we all practitioners plan to be living for 2 months in Northern California and Oregon for the next 5 years to try to have an impact? Like, what are some prioritization things that you've been thinking of?
Yeah, so, that's the motivation for my kind of postdoc research, is looking at this at these fine scales. And so, I was unsatisfied with the different resolutions that we have for these models. So it's either the kind of regional models that I've shown you or just looking at a literal single forest, right? There wasn't much in between. And so that's what I'm trying to do here, is try to look at, let's say, Northern California as a 3 kilometer scale, or we can target federal land specifically, right? And so the idea is that when, where, and how should we do these prescribed burns? So there's an optimization involved, right? So we know that weather can influence this quite a bit. We want to do a prescribed burn when conditions can kind of ventilate the area, but also hopefully ventilate it far from population sources. So it depends where the wind is moving. We can't do this at the top of the mountain ranges in the Sierra Nevada. So it has to be somewhat close to human infrastructure where we can get these machinery and things that we need, and people power there. But a lot of this also is a societal problem, right? It takes a huge number of people to do these prescribed burns, and there's this kind of bureaucratic stopgap that we need to escalate. I know that according to the United States Forest Service and CAL FIRE, they have new proposals and legislation to increase the number of acres burned by prescribed fire to around 1 million acres by the year 2025. And they want to do that every year. Right now, we're doing 10 times less than that. It's really a boutique application. So in many ways, I don't think this is feasible. But what I'm trying to do is create an optimized strategy to do so. And, what does that look like? I'm not completely sure yet. I'm just a person running models in many ways. So if you are someone who is more experienced with the actual on-to-ground experience, that's something I'm also looking to hear from too. But yeah, I'm still excited for this research. Great.
Well, I won't pack my bags just yet, but I we have a few more questions coming in. One from Erica. What kind of weather variables are included in the sensitivities part of the modeling that you presented earlier?
Yep. So that has different wind speeds, temperature, relative humidity. If you're familiar with just reanalysis data, whether MERA2, I'm not sure if you're familiar with that. It's just a series of reanalyses going from temperature, pressure, relative humidity, and this is fed into our convection, advection, and deposition, where advection is the sort of large scale horizontal movement, and convection is the kind of buoyancy of moving those air parcels. And deposition can be more related to encountering blocks of water vapor or clouds and things like that.
Yeah, appreciate that. So moving on in our questions, Shala Hedwal asks, what do you consider a large prescribed burn acreage wise when you're, when you're thinking about having the impact in, reduction in smoke exposure?
Yeah, so in this work, we used the 1,000-acre kind of cutoff. Even could have used 500-acre. I think that would have worked. It's just kind of tricky because the Forest Service and people who actually do these things, it's probably better to do even larger than 1,000 acres to actually prevent future wildfires. That's another thing to consider is what does it mean if we prescribe burn in California 1 million acres per year and we still get mega fires in the future? What you're doing then is also just generating a ton of prescribed burn smoke, and a lot of this falls onto frontline communities. And you're actually not fixing the problem and just introducing another one. So that's challenging. The Eastern United States, they do a lot of prescribed burns, but those are also pretty small because they have a history of doing them, right? They don't need to burn down over 1,000 acres. They do it every year, so it's managed pretty well. So there could be this idea of, do we want to do large scale, really large prescribed fires, thousands of acres at a time? Or do we want to do a slow ramp up to do that? And, what are the costs of doing that? So yeah, I guess I would say 1,000 acres, but those who actually do these prescribed burns might have a more educated threshold.
Yeah, definitely. That's a good working around the table with some dry erase board exercise. Moving on to we have another question from Sumi. Wondering, what have you seen with how much of a difference has it made when the additional weather factors are taken into account from your modeling versus the high split that many of us are familiar with?
Yeah, I guess high split is just very simplified, where you can model a lot of that just using Gaussian dispersion or Gaussian noise. So it just eventually will dissipate due to gravity. Whereas here, we'll see more abrupt cutoffs that are realistic. Like smoke doesn't easily transport over a mountain range unless it's above the planetary boundary layer, for example. You can't do that at all with high split. Or if there's a rainstorm that sits on a patch of land in Oregon or in the rainforests of Oregon, then it gets immediately rained out and you have this kind of discontinuity. So yeah, I think these are important considerations, given that we know that the physical climate system does influence smoke transport. And I think it's just kind of being discounted in a lot of ways.
Yeah, as someone who was on a burn last week and clicked the box for a high split model for our spot forecast, it was not used much in our operations.
Huh.
Apologies to anyone who may be on the call who generated that high split for me. So next question is, how can we verify forecast ventilation? This is from Amber. Is there any is there a climate approach to identifying days where they're more likely to have good to excellent ventilation? Is there a way to reverse calculate plume dynamics from a video of a prescribed fire per se?
Yeah. Let me just look at that message so I answer all points of it.
Yeah, it's jam-packed. It's a good one.
Verify forecast ventilation. So yeah, we can definitely do this. We have LiDAR data, we have satellite data where it's actually quite straightforward to model PBL dynamics, for example. You just use some kind of inert tracer like carbon monoxide. So that's a gas that has a 2-month lifetime. So you can kind of track how it moves from surface of a fire. Does it get trapped within an inversion layer? Does it pierce that inversion layer? So we can verify it through satellite data like that. Climate approach to identifying days, good to excellent ventilation. I think there is, I don't know of a forecast approach. I know a paper last week came out in Nature Comms, I think, one of the Nature journals, showing that prescribed burning windows are decreasing. And one of the factors that they considered is kind of temperature inversion events. So the lack of ventilation, I guess you can consider it. And you can calculate that through these different climate variables that we have. I don't know it off the top of my head. And is there a way to reverse calculate plume dynamics from video of a prescribed fire? So yeah, I think that's super interesting. That would be kind of a data-driven approach that would interest me. And really, there's a lot of problems with trying to model prescribed fire, right? In terms of these models, the data isn't great. We don't have enough data about fire suppression. We don't have enough data about heterogeneous emissions, right? Everyone who has worked a fire knows that even in a single patch of land, you could have so many different vegetation types that is really difficult to model. It's just not all one kind of vegetation. And so, yeah, in terms of dynamics of that, I think that would be possible if you had the kind of video data for that. That would be, yeah, super interesting to think about that if that's something you're actively working on.
Great. So we're going to keep the questions coming until about 10 minutes after the hour.
No problem.
Really appreciate everyone engaging here. And if you need to reach out, Makoto's email is in the chat here. So next question, also from Amber, do we do smoke emissions model reanalysis?
Smoke emissions model reanalysis. I don't know if I can 100% understand, but I'll interpret it how I think. It's the emissions of smoke are actually pretty well quantified. A lot of this is done at UC Irvine, Jim Randerson's group, where they created this GFED emissions, and it's activity-based emissions. And it agrees really well with observations of burnt area, of kind of quickly emitted smoke. So the emissions are actually really well tuned. Sometimes the model that maps the emissions to concentrations with all these different processes are not correct, right? They don't match sensor observations from the EPA, for example. A lot of that is not being able to capture boundary layer dynamics correctly. So we don't know if a fire is really hot, it can actually pierce the PBL and kind of travel long range. But that smoke is kind of aloft and it's not at the surface. And so a lot of, we don't necessarily model that correctly, but the emissions are pretty well characterized.
Cool, thank you. Next question from Annie. Does your research show that wildfires during the traditional fire season produce less smoke, or that the smoke affects a smaller range than a prescribed burn due to the time of year that prescribed burns are generally implemented, i.e. the shoulder seasons?
Mm-hmm. Yeah, so this is not something that I've looked at specifically. I know that there's several researchers at UC Riverside who are working on, who I saw worked on this problem where they simulated basically the same kind of fire in fall versus spring and found that spring produced just a lot less smoke. So yeah, I guess that's how to simply answer your question. So yeah, we do see that kind of effect, but I personally haven't modeled that.
Yeah, okay. So here's another question that that Rachel developed. So you spent a lot of time on environmental justice, and we had those kind of three focal areas around the country that they've been largely left out of the academic conversation in terms of PM 2.5 exposure. And can you just speak to why you think it's important to and why you highlighted them to consider when discussing this air quality component of fire management? And I'll just add that my organization, along with many others, we just put smoke in the air right in one of those areas in New Mexico that your map highlighted. So it's very personally fascinating to me, having just done that.
Mm-hmm. Yeah, I mean, there's the obvious kind of environmental justice aspect of trying to see how those who don't have the voice or resources to do much, how they're exposed and what that looks like. To me, in many ways, I think it's just intellectually very interesting. It's the sociocultural kind of weirdness that we have in America, where environmentalism means something very specific, whereas to these indigenous communities, it means something completely different. These communities have been doing it for thousands of years, and we don't have records of huge mega fires like they did. There's different dynamics where there's records that said the Central Valley was always filled with smoke when indigenous communities were kind of the dominant people in this area. What does that mean for vegetation and knock-on effects on sort of air quality and ecosystem health? A lot of these huge California redwood forests didn't really exist when these indigenous communities were the dominant societies around, so they really altered landscapes very effectively. And early kind of American colonial records show that these settlers just kind of walked in. They just walked through the Sierra Nevadas and everything was an easy traversal because of this routine land management. You can't do that at all. These are huge, dense forests. And within 100 years, we've effectively changed the entire kind of makeup of the ecosystem. And with the advent of climate change, there's many ways we can't go back. So I think it's just kind of, we need these voices, not because of optics and not even necessarily because of the marginalized aspect of it, because I think this is a really important resource of knowledge that we actually really need, because this is kind of the thinking and the culture change that we need, that they should be sort of one of the front runners in who we go to in terms of how we are supposed to correctly kind of manage the land.
Awesome. Well, we're going to wrap it up. Thank you, Makoto. This was really great. We covered a lot of ground. Really appreciate your time and preparation here. And hopefully you'll come back again and show us where your research is headed. But I just want to thank you again and wish everyone well. Stay tuned for the next Southwest Fire Science Consortium webinar or the next Fire Adapted New Mexico Communities learning session. So thank you, everyone.
Yeah, thank you so much.